So yeah, the topic here is attesting the untrustworthy and the mobile request verification at scale. And one thing we are going to be looking at is asking ourselves some very, very deep questions, which is, can we trust the client? So normal request model is usually we having to make a request from a particular client and it goes to a backend service. Most times these clients are usually a mobile application, the web. But on this topic, we are primarily just focused on actually on the mobile side of things. I think that is probably a different thing, right? So we ask ourselves, can we really trust our client? Most of the times we can't. I think the honest truth is really we can't really trust the clients. But we try as much as possible to be able to say, okay, at least have some level of confidence as to say, okay, we can really, really trust this client. So every request we make to the app is more of, are we asking, is it a real device? Has it been tampered with? And is it like a replayed request? All right. So usually when we authenticate users, we do normal like JWT or you're doing OAuth. I think those ones are actually answering the question of, who is this user? And we're able to say, okay, this is maybe a Moniepoint customer or a Moniepoint user, whether it's for personal banking or it's for business banking. We know the KYC, we know all of that, right? But it doesn't really tell us about what is really sending this request. Like, for instance, I mean, the bot can be the one sending you a request and, be assuming a particular user. You most likely would actually know who the user is, but you are not guaranteed on actually, what is actually really sending this request. Can we really trust what is sending the request? So we have a threat model. So the threat model is usually also like we have like modified APKs or IPAs. These are like the app binaries. So usually when you take a app to the store or a user is downloaded your application. So what they download is like a binary on the device. There's also a part where you do man in the middle, and that you can also do compilation attack. Compilation attack is you actually using a modified app, you're running from an emulator, and you also like intercepting the request. So intercepting request comes in two folds. So you are either modifying or you are also doing the replay attack. Just to be able to put that in perspective is when you modify a request, you are, for instance, maybe the request is supposed to maybe transfer under Nira or whatnot, and you just maybe want to modify it and maybe change the user ID or something like that, just to maybe gain somebody else, right? Those are possible. I say another area where we would probably see things like modified request is you want to do things like maybe liveliness, right? And you want to pass in a deepfake image, for instance. Let's say, to give you an example, so I want to be able to scam somebody else, right? So what I can do, again, this is for educational purposes. What I can do is, go to anybody's profile, get your your pictures, take it to an AI model to generate a sort of video for it that can bypass any sort of authentication. What I would do is, as I'm trying to sign up, right, or trying to do a transaction, I can just modify the request, and instead of maybe sending the actual my own camera face, like instead of sending the real one, I probably just modify it and pass in the AI generated video frames, and your backend can maybe just assume that this is the person, right? So, and this is another person. I'm just doing a man in the middle attack, and that goes through. So these are like various threat models. So what we are asking ourselves, okay, definitely we cannot really trust the client in doing all of this. So this takes us to, okay, what we actually want to guarantee. So what we actually want to guarantee is we want to have a real app that is actually signed by us. So what that means is we can confirm that this application is not repackaged. So repackaging an app can also take a form of, I think the IPK, most times people would maybe do obfuscation. But obfuscation is not a really, really big guarantee, to be very honest, because there are a lot of the obfuscation tools that you can actually use to reverse engineer codes that have been obfuscated. So what that means is, and again, when you now run the app, although when you rerun the app, the signature is broken in the sense that it doesn't become an app that we signed anymore, right? But we want to actually verify, okay, the application that is actually making a request to us is the actual application binary that we signed, right? And we also want to verify that, okay, the device itself is a real device. Currently, I know we have two major manufacturers, which is two major stores actually, which is the Google, that's Android, and we have the iOS, right? We also want to verify that it's a real user, then the request gets to our server. So we're asking ourselves like three questions, like is this request from a genuine binary? Is it running on a real or modified device? So what that means is the device is not rooted. I know this kind of things, right? The device is not compromised. The other thing we ask ourselves is, has this specific request been tampered with? So like we explained earlier in intercepting request and modifying request, we want to ensure that, okay, the request that is coming to us, it has not been tampered. So as it left the device is the same way it's getting to us at the back end, right? There is no sort of tamper with it, right? So yeah, to be able to achieve this, uh, it's actually a very hard problem, but to be able to achieve this, we actually depend on the device itself. The hardware itself will give us some level of guarantee. So this takes us to the hardware level, and how are we able to achieve this based on the device hardware? And this is like the most critical part of this presentation. I mean, getting to understand this makes every other part of this presentation very easy, right? And this is where the possibility actually comes from. So for most devices, Android, iOS, there's an underlying computer architecture. I think ARM. ARM stands for I think advanced risk machine. Yeah. Anyway, but basically, it's more like a compressed instruction set, unlike other architecture, like maybe your Intels and the likes. Yeah, right. So this is more not it's smaller in a way, right? So what that means is you can embed they call it system on chip. You can embed a lot of things within that system, within that particular chip. So you can embed your CPU, you can embed your GPU, your memory controllers inside that single chip, right? But then I think ARM provides something else called a trust zone, right? Now, what a trust zone does is more like an extension on in the ARM architecture, where you can actually separate you can actually separate the processors in a way. But the same processor definitely. So it's called so you have like the normal world and you have like the secure world. So you have like your application processor actually um, running separately from the secure world, basically. So we call that the trusted execution environment, right? And that is one way on how we are able to achieve this, in a sense that for things like cryptographic functions and the likes, we actually leave them in the secure world. Just to put this more in perspective, right? So if you look at this diagram here, so we have the normal world. And the normal world in this regards now would be running things like the Linux kernel. Like, so we have for Android, you're running like the Linux kernel itself, right? And it runs in isolation. While the secure world, depending on the manufacturer, most of the time for Android has an operating system called Trustee. And Trustee is its own OS that runs on the TE, which is the trusted execution environment. There's also the Qualcomm. Qualcomm has its own code, and that's the PUSE. Then we have um, iOS. So there's a bit of a difference between how Android does it and how iOS does it. But I think I'll probably go into more details on how is a bit different from Android and iOS. But just have it in mind that the architecture itself gives us a way for us to be able to separate the different worlds. We have the normal world and we have the secure world. And we are able to communicate from the normal world to the secure world via SMC, that's the secure monitor calls, right? I think you can also think about it this way. If you're familiar with some level of how operating system works, the whole idea of I think limited direct execution. So where you have your user mode and you have your kernel mode, right? And you're able to make system calls that would then transfer back to the kernel mode, and the kernel mode can take some kind of operations that you would not be able to take, like more like elevate your privilege, your privilege access, something like that, right? It's almost the same way how the normal world, the application processor, would also be communicating with the secure world, but with the different sort of instructions. Like that's what we call them, the secure monitor calls, right? There's also the part, as I say, different way to do this. So there's a different way to do this as well, is in terms of having a different chip, right, on the device. Yeah, having a different chip on the device. So there's one mode which is called the T, and this really explains the T. And there's this mode where we have a different chip on the device, right? And this just more like makes the security a lot more, should I say, stronger, basically. So in this diagram, what this means is, even though we are on the same chip in this particular diagram, in this particular, in C, we're on the same chip. We just have some sort of logical differentiation between the application processor and the actually where the trusted environment is running. And we have a logical separation of how probably we use the RAM and the likes, right? But it's still the same RAM. It's still the same cache. It's still the same CPU season and the likes, right? But we just have some sort of logical separation, right? More like you have like just maybe probably when switching from the normal world to the secure world, you're probably just changing bits to like maybe from 0 to 1, and you can maybe like change the operations. Then we have the other part which talks about the secure chip. This Android calls this on their own side. They have an API called Strongbox. Now, Strongbox is more like the API to actually work with a different chip on the device, right? For most manufacturers, they also have their own. So for majorly Android, I think it's called, we have the Titan M, and I think Titan M2 and the likes, right? Strongbox is more like an API specification that says that, okay, for us to work, we'll require that the device has some sort of secure element on the device. So for a different chip, what this means is the particular chip itself has its own CPU, has its own dedicated RAM, has its own cache and the likes, right? That's totally different. But it's very easy to just notice that because of this, because of having a different chip, the maybe little downside might be in terms of performance, because we are actually doing a bus communication from this particular chip to this particular chip, right? Or like when it is really within the same chip, where we are just maybe changing mode bits, basically, right? Yeah. So a little bit more on the T. So basically for the T, what we are just doing here is we isolate the execution at the CPU level, right? So again, like I've explained, I think I've actually already covered this a lot. So it's more of a logical separation than physical, right? For the T. And for the T, this is how you probably this is how, look, if you want to look at it from how it really works from a diagram perspective. So you have the non-secure world and you have the secure world. So there's something in the ARM architecture where you have EL0, EL1. Sorry, this is EL3, my bad. So EL0, EL1, and EL3. So the ELs are like execution levels, right? So EL0 is more like the user level. Then we have the EL1, like the kernel. There's another one called EL2, which is more for hypervisors, right? But basically, at the user level, so you're probably, this is where your applications are running. So you have the Moniepoint application. On Android, you usually on Android architecture, you have this hardware abstraction layer that actually, as more like an API interface that actually helps you to make commands on the hardware level, right? So when we say we want to generate a key, for instance, right, we would, talk to the hardware layer. The hardware layer will probably do some sort of system call to the kernel. The kernel will then maybe make a secure monitor call to the secure world monitor. And so for the, like I mentioned, within the T itself, we have an operating system running, which is different from the actual operating system running in the non-secure world. So more like two different processors. So I think Tigris is for Samsung, QC is for Qualcomm, and the likes, right? So I think this gives like a proper view of how the T works. I'm hoping I'm able to paint a very good mental picture of how this works. Then for the strong box, it's entirely separate. So you can see that on the strong box side, it has its own RAM, it has its own secure storage, and the likes. We'll still see how this helps us to be able to actually get to where we're going to. So similar thing for iOS. iOS has what we call the secure enclave, sometimes called SEP, which is secure enclave processor. So secure enclave processor, it's more like Android, Strongbox. Remember that for Strongbox, you have a different chip. However, what Android is doing in this case is actually having the chip more like a coprocessor, basically. That's what they call it, a coprocessor. So a coprocessor sits on the same chip, but totally isolated in the sense that the secure enclave also has its own CPU, has its own RAM, and the likes. I think that's just the major difference. Now, you might be wondering how, if this is something like, if there's something like how maybe Apple Pay works. But yeah, something similar. But I think there is a different chip for things like Apple Pay, Google Pay. I think those are like the NFC secure elements, right? So they are actually totally separate chips for it. But this, I think, is for more like other cryptography functions and the likes, for security and attestations and all that. Why do we need this, or why does the hardware bound keys really really matter? Okay, it matters a lot. So I'll give some context here. Why we were trying to internally, we also had a lot of should I say security issues. It's one thing to build an application. It's a whole different ballgame to actually secure the application. Like it's so when people say fintech is really hard, it's hard because it's not just about the fancy things you see on the screen. There's a whole lot that happens behind the scene. We did have like a lot of issues as we grew as a company. We've had scenarios where people maybe use emulators to do a lot of funny things. We've had issues where people send requests that are not even coming from the device, and we've always known that okay, we can't really trust the client, and we're looking for a way that we can really at least have some level of confidence to say, okay, this guy, this person, the thing that is making this request has some level of trust. And we thought about embedding keys on the app and doing obfuscation. And the question was like, the people that are really attacking us are also a lot more advanced, right? In the sense that, just, add coding a particular key on the app and, updating the code doesn't give any sort of, guarantee, because an attacker that is smart can do a few things. An attacker that is smart can use some certain hooking tools. Again, for educational purposes, there are tools like Frida. I think there are tools like Exposed that you can also use to do things like, like hooking, right? So what I would do is you can actually see all the method calls that are being called as the application is running, and you can read the address spaces to actually find out what is happening. You can actually just extract the key that's on the device. Like, it will probably be very easy for um, an attacker that is really, really smart. So we went back to the drawing board to actually look at what the device itself can really offer, and that's when we found out, okay, we can actually use hardware backed attestations, right? And the purpose of having hardware keys is majorly because you cannot extract it. I think so. That's like one of the major purposes is having non-extractable keys, right? So keys that you can only use on the device. You can only use it to encrypt, to decrypt on the device. So you cannot take it outside of the device. So even if you maybe root your device, right, your operating system, as you can mostly do with things like on Android, basically. I know you can maybe do it with iOS, but I think it's a bit harder. But you can do it with Android easily, right? And you can then, extract keys, but with hardware bound keys, it's a little bit harder actually, right? So that was what really gave us some level of confidence. I said, okay, I think we can actually maybe just we can actually do this. So this would probably be a see it like more like the hardware chips, or the secured world is more like a registry that gives us a sealed envelope, right? So whenever you want to maybe make a transfer, whenever you want to sign in, you want to onboard, you tell that particular secured world to say, okay, I want to do this. Can you help me seal this? Right. So it stamps it, and we take that and we send to the backend. From the backend, because it is sealed, we are able to actually verify it and say, okay, this is actually coming from an actual device, right? So I think that that's one of the major things. When we create a key on the device, so I'll try to explain how this would usually work. So for us to be able to do attestation, what that means is we're actually creating a key on the device, right? And that would mean that we can also get the certificate chain of that particular device, right? So we have the concept of concept of chain of trust. Like, I think you probably also find this in normal public key cryptography, right? But for every device that is out there, you can also, when you create a key, Android, iOS, you can actually get a certificate that you can also link back to the actual root certificate, right? So I'd probably just use this as an example, just to give you a very good picture of how this works. So Google would most likely have Google's like the certificate authority here, and would have its own private key somewhere down within their servers. Nobody can have access to it, and all that. So where devices like maybe Samsung, Techno, I don't know if they're compliant, but let's assume they're all compliant. When they make their devices, they also maybe create their own intermediate certificates. Take it to Google, Google signs it, right? At the end of the day, during factory, they would bound a sort of attestation key within the the device. So this can be within the trusted environment or within the chip, and all that. And when we also not try to, what we do, what you actually want to do is, you would want to, create a key and get the certificate, the attestation certificate. So when you do this, usually you probably want to get a non, you probably want to, fetch a nonce first, or NONC, just to be to prevent things like replay and the likes. Right. Well, basically, you generate the key and you get the certificate chain. So the carrier chain will usually contain the roots, intermediates, the device intermediates, and also the leaf certificate. Sometimes you can probably just get only three. And if you understand how certificate chains work, it means that usually it's always like the root would have to sign the intermediate would have to sign this, the your leaf certificate is to be signed by the device intermediate. So this way, when you're also trying to do a verification, you can actually verify the chain of trust to say, okay, was this guy signed by this guy? So probably doing verification with the public key to say, okay, was this guy really signed by this guy? Then you go back to this guy. Then the root certificate, it signs itself basically. So you probably just check that, okay, this guy was actually signed by its own public key, something like that, right? And I think that's really what happens, and that gives us more guarantee in the sense that it's also very, very important to mention that so the attestation certificate we get would contain the actual package name of the device, the signature of the device, the signature of the application rather, right? It also contains something we call the root of trust. So the root of trust is it tells us whether this bootloader has been unlocked. It tells us whether this bootloader has been verified. It also gives us some other level of other sort of information that we can actually use to uh, get to verify that okay, this device it's okay. The application itself is running on it. It's signed by us and the likes. When verifying the certificate chain, there's something we also do. So it's called the CRL check. So CRLs are like certificate revocation list, right? You would usually there's actually a repository or an API you can call to actually get a list of all certificates that have been revoked. Now, why is there a certificate revocation list? Is because so security is not should I say it's not permanent. It's not it's not fully really it's not something you just solve and everybody is is happy and there's really no breach, but there is, right? And that's why to a very large extent you still would not still trust the clients, right? So most times some people have the school of thought that why do all of this? Is the user's device, you can never trust it, right? But again, if you are building a financial application, I think you would not support that school of thought. You probably want to be like, oh, I will still prefer to have some level of guarantee that somebody that is really communicating with me is valid, right? So so we do this. We do a check. We check the certificate revocation list. So these are most likely, for instance, compromised keys. Let's say, for instance, the attestation list certificate, the attestation key that is embedded on the device, in it, even within the trusted environment, is compromised. It's sadly, it's a possibility, right, that things like this can actually happen. And I'll probably explain some ways that these things can actually also maybe happen. So once it is realized that some of these things have happened, so in most cases, it gets reported and it's added to the verification list. So what we do is when we actually receive the attestation certificate, we would also try to say, okay, has this certificate been revoked? So that's by us checking the certificate revocation list. And that brings us to the full attestation flow. And so what we do is it's pretty much very simple. So first of all, we request for a challenge or a nonce, which is usually very dynamic or random. I mean, I'll probably not advise you. You can choose to maybe skip this, but it's recommended that you actually use a nonce to avoid some sort of replay attacks, right? And we generate the key pair. So we generate the key pair for iOS. We are using the secure enclave processor. For Android, some devices come with Strongbox, why some devices don't. I think from Android 9 is where we actually have things like devices that actually have a separate chip secure element for some cryptographic functions and all that, right? So there are some devices that don't have. So it sometimes puts you, especially for Android, it puts you in a position where you have to find a balance to support a lot. So Android has its own hierarchy. So the hierarchy is Android has some level of software attestation key. And what this means is this actual key is actually just embedded within the probably just within the code base, right? It's just there within memory, basically, right? And this is very easy for anybody to extract, right? Attackers can really extract this particular key. Then you have the trusted environment, that's the TE. Then you have Strongbox. So Strongbox is like more like the most secure. With a little bit of should I say performance drawbacks, right? The secure enclave, I think it's pretty much. I mean, I've probably not maybe heard of it being slow in any regards, but just a little bit of difference on how you probably get an attestation key from both, right? For iOS, you most likely on the device have to make a call, and the underlying framework will probably make an API call to the Apple service to actually get a key, and you can be throttled for this, right? So usually when you roll out for iOS, you probably have to do it in bits, so you don't get rate limited, right? But for Android, there are also some few options you can go with. You're usually using play integrity, but we choose not to use play integrity for some reasons best known to us. But yeah, you can also generate keys on Android, whether you're using whether you have whether it is the software level, the TE level, or Strongbox, depending on what's available on the device. For TE, you probably start supporting things like Android 7 up above, right? Although TE has actually been existent for quite a long time, but I don't think the larger support for it, I think for asymmetric keys and the likes, were only available to like Android 7, right? But yeah, the long story short is that ideally when we request a challenge nonce, we generate a key pair. To actually request for Strongbox, when generating a key, you have to actually specify and say, okay, use Strongbox, right? But then if the device does not have Strongbox, to try an exception, right? You have to handle the exception as well. Maybe fall back to the normal hardware level. If the device does not have a sort of is not TE as well, probably fall back to software attestation. But it's very important to also know that when you actually receive the attestation certificate, you are able to actually know if this is hardware or software. So within the certificate, within the attestation extension certificate, you have what you call software enforced or hardware enforced. So you're able to actually read to say, okay, this is a software attestation and this is a hardware attestation. And depending on your threat models, your fraud checks and the likes, you can decide what you want to do with it actually. So yeah, we usually get the attestation key, then we would call an endpoint. So more like we're sending this after we've attested the device, but more like we're calling an endpoint. It's okay, guy, attest this device. The communication channel that we use to also, attest the device is also pinned. So if from I don't know, I think most people understand what certificate pinning here means. But for lack of uh, just to explain it, it's more like your server usually would have its own certificate. So TLS basically. So you have your certificate itself that you've also maybe registered with the certificate authority and the likes. You have your own leave certificate, your intermediate, yada yada yada, right? Same way on your devices, you have something called like a trust store, right? Usually when you have a trust store that contains a lot of certificate authorities, right? You can also install your own user certificate authorities. So when you are making an HTTP call, what usually would happen is there's some sort of a verification to say, okay, this certificate, this particular certificate, do we have any sort of authority that actually so that's a support it, basically. But in this regard, what we are doing is we are trying to say that okay, when making this API call, we only want to trust only one certificate, basically, which is our own server certificate, right? Now, what does this prevent? It just basically helps you with things like man in the middle attack. And because if I want to do a man in the middle attack, what I'll probably basically do is, tell you to install my certificate, my own particular certificate. And if you install my certificate, what that means, I can actually see your traffic basically in plain text, right? I see your traffic in plain text, and I probably modify it and forward it back to your backend, so you would not know. So I don't know if for in those days probably we had a Nokia device or even Android device. When you're trying to, even your browser, when you're trying to communicate with a service that the certificate is not trusted, you get this sort of warning that, oh, these certificates, we don't trust it. Do you want to add it? So if you, and those days, because we don't really sometimes even know about these things, like you just want to, go through the website or go through the application, it probably just says add, I trust, right? So you can actually be an attacker, actually, giving you his own certificate to install, and you can, when you install it, and you seize all your traffic and the likes, and from there, things goes kabosh, right? So we pin to our server certificate. And so what that means is during the TLS handshake, we would actually also check the, okay, the server is saying, okay, we're saying hello, hi. So the server also gives you a certificate and say, this is me. So we check and say, okay, this guy, is it sort of the, is it our actual service that we're talking to? If it's not, we bounce the request, right? We don't send the request. And to be very honest, it's just an extra layer to help. It doesn't mean that without this, it is broken, right? It doesn't really mean, but this also just adds a different layer of sort of security to say, okay, we are actually talking to the right backend service. Then within the backend service, we would then do all the whole, yada yada yada. So we'll definitely do the verify the chain. And we've got to confirm with the certificate revocation list to say, okay, has this been revoked? We check the security level. For instance, is this a software enforced or hardware enforced? It's very important to know that, okay, we actually just do this behind the scene. Like, we really just take your attestation certificate and tell you, okay, we've gotten it, that's fine, right? Then yeah, we would definitely now store the public key of the device. Remember that we've gotten a chain here, right? We've gotten all of this. So within this guide, so we have your public key and the likes, and this is unique per device, right? And this is also a very, very way to actually uniquely identify certain device. But I mean, but then you probably want to do it carefully. But yeah, so we store the public key of that particular device. And the reason why we're storing the public key is just so that, okay, next time this user is coming, we are also able to see that, okay, you have we can verify your request, we can do a whole lot of of that. Yeah, I think that's it. Then when you make an API request, this is the other path. So after we've been able to say, okay, we have your we've done the attestation. So attestation is more like saying that okay, we do now have something to say that this device is either valid or not valid. Something very important to mention within the certificate is when we're trying to verify the certificate chain, the to verify that the root certificate is also valid, there's also a public, Google has the public certificates opened. The same thing with iOS, Apple. So the public is outside. So we actually use that public key to actually verify that, okay, this is actually Google signed root certificates. Yeah, I think that's pretty much it. The only downside to some of this would be, for instance, we have separate, should I say, there are other devices. For instance, I don't know if anybody has heard about Graphene OS, but I think that'll probably be a different topic. So Graphene OS are kind of like devices that maybe they don't care about Google per se, right? So they don't use Play Store, they don't use anything. They also have their own public root certificates. So depending on the device you want to support or the OSs you want to support, right, you can also go and get their public root certificates and use that to actually verify the roots, basically. It's really not that complex. Then yeah, the request signing flow. This is after we've done your we've done attestation. So attestation is basically just saying, okay, we are able to prove that this is your device, and whatever your device is, right, we can make a decision on it. So we're able to tell, is your app modified already, right? I couldn't maybe go through the full internals of what contains within the certificate, but most certificates, I mean, you have your different formats. So let's say you have your X.509 certificates. So what we basically just do is we actually pass the certificate. So probably I should explain just that a bit. So we probably pass the certificate. So your certificate are usually in certain sort of encoding rules. So you have your DARE encoding rules, that's DAR. We have I think BAR, basic encoding rules, and the likes. In those certificates, you usually would have things like let me see if I can get an example. So you have like sequence, different sort of data formats that you can then use to you can actually now read the data within it, basically. Just to give an example, I'll just paste one here. So this can be like an example you would have. So you have like this can be a certificate, basically. So you have a certificate, then you have a sequence, you have the subject, the issuer, the public key, the validity, the extension. Now, for Android, the particular attestation certificate lives within the extension. So that's actually extension number. I think is 0.17 yada yada. It's a long number. So you actually have to pass the certificate. So more like you decode it and read all of this. This is, if you're interested in how certificate works, that's the ANSI and the likes, right? Abstract notation syntax. It's pretty much very interesting. I mean, it's more like the way you have your JSON, right, which is very popular. There are also other different data syntax or formats, right? So you have I think you have DR, BRs, and the likes, right? And I think DR is a lot more strict than BR. So basically, for the particular attestation certificate, so when we get the certificate, so I think the leave certificate most times, you would find the attestation certificate, right? And you would basically just go to the particular extension, and you're able to actually read the attestation details itself. Yeah, so you read the attestation details. again, reading all of this requires you to pass it, get TLVs, tag length values, and the likes. A lot of byte operations and all those kind of things, basically. So you read that, and after you've done that, you get the actual details that you need. Like I've explained before, for Android, you're getting things like your root of trust and the likes. For most times, we actually also experience that some devices, the certificate validity is usually very, has expired, something like that. So you treat that as depending on how your organization probably would want to treat, sort of certificate that have expired. But usually, yeah, the lead certificate should most likely be recent. But again, there are a lot of devices, and the behaviors are usually very, 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 very funny, right? So yeah, that being said, yeah, the request flow, back to the request flow, is once we are okay with, we've been able to do the attestation path, we usually would now be able to sign a request. So remember that we've created a key and we have a private key that is now probably sitting at the hardware layer, right? So we also guarantee that one of the guarantees we have is that, okay, this particular key cannot be extracted. So at least cannot be extracted. I say that in quote and unquote, right? So, but yeah, very hard to be extracted. Maybe that's the right word to use. So what we do is when making a request, let's say we're making a login request. Usually we use JSON to communicate between our app and the backend services and the likes. But yeah, so what we do is we would usually build a canonical representation of JSON. And the reason why we are building a canonical representation of JSON is because the format of JSON is really not guaranteed, in the sense that if you send me a JSON and you have ID at the top, let's say we have this JSON, and you have this one, and you have this right. If I send this to the server, definitely the server will probably have to deserialize this again. Now, if the server is deserializing this, you never can tell that the format it will deserialize to is probably deserialized to something else where you have user, yeah, and ID can be very, very possible. And when dealing with things like we're dealing with cryptographic functions like you're signing the request and you're verifying, everything is important. It means ordering is very important, right? So what we do is build a canonical representation of this. There's an RFC for JSON canonicalization. I think we actually read that. So basically, you're putting things. You're probably just maybe putting things in some certain sort of order. Maybe you're sorting the keys and the likes, just to ensure that everything is in order. So the backend also does the same thing, follows the same algorithm, and is able to actually arrive at the same canonical representation of this, and then verifies it. So that's basically it. So basically, we would generate a canonical representation of the request, and once we've done that, give me a minute. So once we've done that, we sign it. Yeah, we sign the request. Most of the time, when doing this, we probably just add something on the header that contains maybe the signature, the timestamp, the random generated nonce, as well as the attestation ID. Usually, when we attest, we actually would maybe have some sort of attestation ID to it. So for most of the requests we would make, would actually also sign it. And however the formats, you could use anything, maybe a X request signature. We also usually will have like a timestamp and also a nonce. Timestamp and nonce are able for us to be able to detect things like replayed attack, stale requests, and the likes. So when this gets back to us, So when it gets back to us, definitely. So we have the attestation ID. We can actually fetch the device public key. We reconstruct the canonical string. We check the freshness, check replay detection, and and all this happens within like less than maybe 10 milliseconds actually, and we're able to forward that back to the gateway. So our internal model for this is, so all requests go through an API gateway that we internally have, and there's some sort of middleware that would, ideally verify every request, right? There are two modes to this. You can either directly block on the gateway or allow the corresponding backend service to decide to make a decision on what they want to do. So what that means is at the gateway, we are able to now talk to the service to actually do this in less than in a single digit milliseconds to verify that, okay, is this valid? Is this application valid? Yeah. So it gives you all of those response back to say, okay, this is valid or this is not valid. The device is, maybe compromised, or the device is not trusted. The application was installed from a very, very random source. Or the application has been modified and all those kind of things. So it gives back that, and the gateway can actually propagate all those informations as maybe either propagation back to the backend service, and the backend can either decide what to do, or the security team can also decide that, okay, we would really just want to block this request because it doesn't really make sense to us. There are a few requests that you probably see, and you probably just agree that, okay, we should actually just block it, because especially for things like modified applications. But sometimes it's very, very agreeable. But in my own opinion, not agreeable. That some people, there are some use cases where people want to use, modified apps. You would find a lot of, I mean, in our own case, we've actually really seen a lot of people use modified applications, right? So these data are really literally very available to us, and we can, decide to block, or decide to add some other sort of checks to say, okay, is this valid or not valid? But you find a lot of cloning applications. The one that sticks to my head is I think multi-space, right? There's an app called multi-space where you can have, and again, this is for dictionary purposes. I'm also use this test of applications, right? But yeah, there are applications like multi-space pro and the likes that you can actually use to clone application. What this allows you to do is run multiple instances of those sort of applications, right? So you can actually run multiple instances of X app, right, on the same device, and you are able to either create multiple accounts and the likes. So for the banking industry or the fintech applications, it's a very good thing to really have. And I think one other thing we would say we see most of the time is also emulators or routed device. At the time, it was also a bit it was a little bit hard to sometimes maybe detect emulators, because emulators they are really very, very high grade emulators that have sometimes very hard to detect. Sometimes what people do is within the application itself, which again, most people have different school of thought, but what I held on to mostly was that it was going to be very, very risky to just check for if the application is rooted right on the application itself and just block the device. So so that's how some other people would do it. What that means is, on the application itself, what they do is they would check some path within the application or the operating system itself to say, okay, does this user have access to, maybe as like a pseudo access, basically, right? So if these are pseudo access, you can maybe just assume and say, okay, if you have a pseudo access, then it's like a root user, definitely, right? And those kind of like check some some path in the the system itself to say if the user has access to those kind of part, maybe like the as USR being those kind of parts to see does he have access to it and those kind of things. So if you have access to this, you can then maybe like um, um, come to a conclusion that okay, this is definitely a a, um, a this device is probably rooted and the like. You can also maybe directly just check for the application signature directly on the device and say, oh, this device is modified. But those are not very, very strong methods, right? Those are actually very, very weak methods. Again, for the educational purposes, there are tools that you can actually use to root the device and at the same time use those tools to hide yourself as being having root access. There is Magisk, Magisk, if I remember very well, like Magisk, something like that. Yeah, that like you can actually use to root a device and also hide that you're rooted. Another downside to that approach is that there can be really, really large false positives because if you really just check if the device is rated on the device and you just decide to block, you can, especially if you already have like a large customer base, like Moniepoint, for instance. Yeah, you have a large database. You don't want to do something where you just make the assumption on the devices. So if it's not even secured, and you just block your users from using your app, right? Because again, the African market is a bit tricky. We have more of devices like ITEL, Technos, and the likes. And some of these devices sometimes can be their OS can be very funny, right? Or they probably have been tampered with or rooted or something like that. And they can be sometimes, it can sometimes be genuine users, right? So you don't want to, outrightly just, check on the device and block the device. So you'd want to maybe do something at least remotely possible to get a lot of data and make a decision on that data to say, okay, is this it is valid, is it not valid? Should I block this user? Should I not block this user? Should I, just um, you know, allow this user to chill a bit, allow him later. Whatever you'd want to do with that information, yeah, you have um, the power to do that. Yeah. So again, some of these things are also very, very, very just very, very similar with how iOS actually also works. It's just very similar. iOS also has its own roots public certificate that you can also use to verify. The only difference I think with iOS is you usually would not get a certificate chain. You would usually get just a particular certificate itself, right? That you can check the I think the RIPD hash, the AGUIDs, and the likes, right? That would also give you information about if this application is mine, if the device is is not compromised and the likes. So, but then most of our user base is actually Android, so it just makes sense to. And again, the methodologies are a bit similar. So I will round up with maybe giving like a full overview of this. So I think this is primarily everything into one full O slide. Then I would then maybe let's talk about some of the breaches that has happened. So yeah, why we've done this, it doesn't mean that, again, it doesn't mean that security is 100% guaranteed. I mean, to some extent, hardware attestation is a lot more better than having nothing. And hardware attestation is really, 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 really very, very strong, right? But has there been sort of, groundbreaking, breaches, especially on CE, right? Yes. And I think that is probably what led to, having a separate chip on the device that you can actually maybe have that has its own CPU, has its own RAM and the likes. So I think more popular breaches around
around T, mostly side channel attacks. So side channel attacks are like attacks that how do I explain it? So side channel attacks are like attacks that questions the how. So let me explain. So let's say you would normally do something or take a task and you'd get a result. Maybe 1 + 1 is 2, and the likes. Or you're typing something on your phone, you're typing your pin on your phone. I think that's a good example, right? And at the end of the day, you've logged into your device. So side channel attacks is asking the question, okay, how did you do that? Right. So from those sort of mechanisms, I can actually maybe infer the pin you've typed. So I'm probably looking at, okay, looking at your device, I can look at, okay, what's on the screen, which places your finger really touched, right? The pressure on your device, those sort of things. Those are some of the attacks that's like what side channel attacks are like. And that has really happened with TE, where there have been reasons where they've been able to, at least I think particularly for TE, where they are able to maybe have access to the keys within TE. Most times around I think timing attacks. So timing attacks are like you probably, what the attacker will do, again, a very maybe advanced attacker would probably have to sit down and observe all the operations happening on that particular system. Because T still uses the same CPU, it's just a logical isolation, right? You're able to actually look at the CPU cache and maybe look at everything that's happening. Look at and monitor the time. A very good way to explain timing attacks is okay. Let me do this. Let's say, for instance, we want to compare, and this is just the basics of trying to explain timing attacks, basically. But let's say we want to compare a name, for instance. Let's say my name is Paul, and I want to check, or let's say you send me a name. You sent a name. Sent a name, right? This is what you sent to me. And I want to compare if the name is equals to, Paul, right? Now, what the attacker can do is, sends you random values, right? And usually the way the equality would work is it's going to check, for instance, if I send, for instance, if what I send as a name is for lack of I send Nathaniel, for instance, right? Or let's just say Nat, just to make it yeah, let's say I said Nat. Because N and P are not equal. All right. What that would mean is it will fail. And let's say each of these fills in, each of these takes 1 ms times 4. That's 4 ms, right? Right. So if I send this guy, it fills in less than 1 second. So let's say I change it to PNAF. So the timing attack is me observing the time that this is happening, and I'll be able to now infer that, okay, it now took me 2 milliseconds before it filled. Now, this tells me that P and A is correct, but T and H is not correct, right? So I keep on, modifying this. So I see that, okay, this guy now fills in 3 ms, right? I do this until I get 1, right? So these are some of the, these are like major attacks that has happened within T that can be used to infer what is actually happening within T environment, and you're able to maybe use that to get the key that is probably used to encrypt or decrypt and the likes. So those are some. But then I think over the time there's been major improvements, and most of the time these are usually maybe software bugs, actually, maybe within the T operating system itself, right? I think again, for majorly things like timing attacks, I'm very familiar with things like constant time programming. I think we actually used it in the we actually used it in one of the in August. This is our attestation of service where we're actually trying to compare. I think I can't remember what we were comparing, but I know Rust has a library for constant time equality. You can so basically what you probably want to do is instead of using an equality check where you're checking each per one, you're probably checking everything at once. So you don't stop at the first character. You just compare everything at once. You just know, okay, so whether it fails, whether it passes, it's going to be still maybe 4 milliseconds if it's 4 characters, for instance, just as an example. But there's also been some other sort of attacks. They are a lot more advanced. I probably am not very, very familiar with maybe checking how the device is using the power and the likes. Again, I think one very important thing about security, again, from a mobile perspective, is, or generally actually, is that to me, it's more of how long will it take. It's more of a question of time than a question of you can never break it, right? It's more of a question on time. So what that means is, if your system or your application is easily broken in maybe an hour or 30 minutes, and then it's not really not secured. So if an attacker that is not even really that smart can just take your application and do a lot of fancy things on it, then it's really not that secure. I think it's more of it correlates with time in the sense that, okay, before you will be able to actually even break this, it'll probably take you years, right, to be able to do. I think it's almost the same thing with some of cryptography and the likes, where to be able to decrypt certain things, even though you're doing a brute force attack, will probably take you longer. I don't know, maybe quantum computing will probably change a lot of things. Like maybe especially on the Bitcoin side right now, where there's already a scale about quantum computing, trying to understand it. So, but yeah, one very good use case of doing hardware attestation is also actually within things like the cryptocurrency hardware wallets. So basically, if you're building things like financial systems, right? It's something you should actually think about or put in your stack to be able to take out the bad actors. I would be very honest. There are bad guys, and there are a lot of bad actors outside there that are really, 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 their work is actually to break your system. And not just to break the system, to make money out of it, right? And there are the good ones, fair enough. I think we've had scenarios where some good ones who have maybe done some things would probably send you an email and say, "See, I did this, and this is how I did it," right? And I think that's how maybe security is looked at. I don't think there's a school of thought where people think you have to really hide all these things. Don't let people know what you're doing. But that's more of obscurity than security, right? Maybe a good security system is saying that, okay, this is what I do. If you can break it, please let me know. And I mean, not like everybody will let you know, though, but if you can break it, let me know. And we would maybe make adjustments to it. Yeah, I think I've done justice to this. I've taken a lot of time. So I don't know if I would if there are questions for me to answer, and I will take questions now.